Okay. Hi all. Thanks everyone for coming. Today I would like to talk about reactive web applications and mostly about what hides behind this buzzword, which has been popping up in the media quite actively over the past months, years. So what I want to talk about is first give you a bit of theory about how web applications have evolved over the past 20 years or so, how hardware has evolved, and then I want to put aside this theory and do a bit of live coding and code a small reactive web application to show you what it means beyond the buzzword. And if there's time left, I would like to talk about deployment, load testing, things like this. If you at any time have any question, please shout. You really need to shout because I cannot see you so much because I have light coming right in my eyes. So just don't hesitate to interrupt me if you have any question at any time. All right. A few words about myself. My name is Manuel Bernhardt. I'm a freelance software developer. I live here in Vienna. I'm mostly working with the web, front end, back end. And for the five and a half past years, I've been working mostly with the Scala, the Play framework, Akka, and I've written a book called Reactive Web Applications. I've done writing the book. It's going to come out in print in April or May, probably. And it's on the topic of reactive web application. It has 390 pages, and I'm going to tell you everything of these 390 pages now in like the next 50 minutes. So, listen carefully because I'm going to talk really, really fast. So first off, I want to start talking about well, something went wrong here, but it's mostly a short history of web application architecture evolution, but mostly it's deployment architecture. It's not sort of it's what you have to do on the operational side of things. But don't quote me on this thing because it's a very summarized version of the evolution. But the first thing what we had in the good old days, and this is something I'm really missing sometimes, is you had your HTML files because you didn't have HTML because DOS only had 3 letters. And then you had your obligatory construction GIF image where, because your site was in construction, so you needed to have this, and some of the images were broken. And so you had these files, and all you did to deploy them was to take them and FTP them to a server, and you were done. So no headaches, a few arrows, but not really anything too complicated. Then fast forward a few years later, and we had something like this, especially I think in the Java space, this is pretty popular. Who has worked on exactly this stack with these? Exactly, yes. So I think this is fairly popular, still popular now, and it's fine. You have your front-end web server, you have your Apache Tomcat in the middle, and the database, and you have 2 arrows, and it's not too bad. It's still fine, and you can deploy this, and it kind of works. And then fast forward a few more years. Who can tell me what comes next? That's too fast. A bit in the middle. What? Ajax? Yeah, something like this, but no more ideas in terms of our deployment architecture. Yeah. A bit later, after WebSphere, after WebLogic, something that is a buzzword and still, I think in the enterprise world it's catching up about now before microservices. No? So what I mean is cloud. Oh, sorry. So this is a project I worked on. I didn't build this, but we migrated away from it. What you have in a cloud thing is sort of the freedom to involve as many moving parts as possible, so you end up with something like this. You just plug everything that comes your mind together, and you end up with having something that works, mostly. What I'm saying really here is when you look at this, what you see, you don't see anything anymore. What you see is you see a lot, or you don't see them anyway, you see a lot of arrows on this thing, right? And these arrows in this graph, they represent, most of them, they represent network communication. And keep that in mind. I'm going to come back to this in just a moment. Yeah, the next thing, as you have guessed it, is microservices. I'm not going to mention Conway's law. I'm going to leave that to the other microservices talk. But what I want to say is, microservices is something, if you look at it, and so I found these images describing microservices, and I thought, what can I find that sort of mirrors this in a way? So I did an image search. You can put an image as an input kind of thing of a search. And I found this which is the flying spaghetti monster, if in case you don't know it. It's a Rastafarian religion kind of thing, I think. And what I want to say is sort of without wanting to go too deep into it, but it's not because you have microservices that suddenly all of your problems are going to go away, because the complexity is shifted in the relation between all of these things. And just one thing, I think that if you don't have a team that has at least 30 to 50 people, maybe don't go in there right away, because you will need to manage this complexity. And this complexity only happens at a certain scale. I think Neil Ford said this morning, this is something, you have to be tall enough for it to make sense. And I see a lot of people hopping on the microservices train, and you can see the wall is coming closer because the complexity is there in all of this, in all of these connections, in all of these operations overhead. And now I will stop talking about microservices. What I really want to say is that the trend clearly goes towards having more network input-output, more network I/O, and we picture ourselves being there as the masters of this network and having to manage this complexity. So I trained as a telecom engineer. I've worked at a telco, and this is the theory. In practice, your network, that's your network in practice. Anyone who lives in Vienna here, who has been taking the U4 and been on the mobile phone on a call at the Lengfeldgasse, knows what I'm talking about, because usually what happens is your signal is gone at that stop. And so networks, they fail. They're not, that's just how they are. So really the challenge is how do you build reliable applications on top of a flaky network? Since now you don't have a choice but to use network. And so that's where reactive architectures, or the architectural pattern of reactive applications comes in. You want to build something that's there for the users, that's fast, because if it's not fast, they're going to go away. There's no chance you're going to retain anyone on the web if your website is slow. And you want something that's there, that's available. For this, you need two things. You need it to be resilient. So in case of a failure, for example, one third-party service dies or a database dies, you don't want the whole thing to crash. You don't want the whole application to become unavailable, because you could possibly isolate the failure. You could redirect whatever the third-party service was doing to something else, to a failover. So you want the whole system to be resilient, and that without you having to get up at 3 in the morning and sort of reroute the calls. That's not something that's going to work very well. You also want your application to be able to withstand, increased traffic. So if your application is featured in the New York Times or the Guardian or something like this, and then suddenly everyone looks at it at once, you want it to be responsive. You want it to be there. So you want to be able to detect that your traffic increases. You want to scale out on more machines, and then you want to scale back in later on, because if you don't scale back in, you're going to have more expenses, and that's something that you don't want necessarily. And so the underlying idea here is that everything is message driven. I'll come back to this in a minute. So now that I've talked about software, let's talk a bit about hardware, because we cannot talk about evolution if we only look at the software part of things, because otherwise we end up like this. Notice the never obsolete part up there, with AOL 5 nonetheless. So I think that's That's kind of great. So what I want to say here is we have our hardware evolves all the time, so that it's a good idea while we build applications, especially if we want them to last over several years, to look at how our hardware is evolving as well. So in terms of CPUs, we don't talk about single core or dual core or multi-core anymore. We talk about many core CPUs. I have one of these guys at home. It's a Tilera Cadmium board. It has 72 CPU cores. I mean, it's a CPU that has 72 cores. So you have 72 hardware threads, which is pretty awesome because you can do things like really real-time image analysis, or if you build drones or things like this, you are in real time. You really can do things. It's awesome. If you look at the new phones that we have, the latest phones, they have 8 cores. That's great. There's just one little thing is that as developers, we sometimes, or we rather often, we don't really make use of this. And so what happens is this, There's one guy and everyone is, they're just hopping around awkwardly. Just look at them. But that's what happens when you build something and you don't think about how am I going to use all of the hardware that's available to me. And that's what's happening today. So most of your phones with 8 cores, well, guess what? CPU 0 is there to do all of the work. So that's one thing here. The other part where we are going to see an evolution, and that's more for later on, right? But this is optoelectronic CPU where you see the communications on the board done with optics. And that's where I'm saying that we will probably see in, 10 years or so, machines where the network latency part is becoming less of a problem as well, because we're going to be connected much faster to the network, at least inside of a data center. Outside, it's going to take, I don't know what's going to take, but it's going to take longer. So these are things that we have sort of to keep in mind. At the same time, memory is also evolving. There's a cool website, it's called yourdatafitsinram.com. So what you can do there, you go and you say, I want 6, and you choose and you say terabytes. And then it says, yes, your data fits in RAM. And if you click on the yes or the your, you will be redirected to, I think HP and Dell, they have these machines where you can just, buy a server and have 6 terabytes of main memory. So if you have a big data problem that's about the size of a few gigabytes or hundreds of gigabytes, that means that you don't need a hard drive anymore to do all the intermediary steps. This is where things like Apache Spark come into play, where you can do all these computations that Hadoop is doing on disk. All of these steps, you can do them in memory, and that's of course much faster than what you have had traditionally with Hadoop. And that sort of really changes the game, if you think about it. Also, something that I think many people missed, so I was sitting in a cafe in Zurich last summer when this came out. There is a new kind of memory, the first one since '89, after NAND flash. All what we have until now was NAND flash, and now we have a new thing. It's called, what's it called? X-Point. Well, it has a fun name, but nonetheless, it's 1,000 times faster, and it's also persistent. So this has a huge impact, especially when you think of CPUs, because suddenly your caches, your CPU caches, can be much higher, and they're persistent, which means that you can, if you have a machine like this, if it's well built, you just power it off, the thing has no more power, you plug it back in, the state is there where it's left you, also in the CPU, everywhere, which is pretty awesome. And so this is also going to change the game quite a bit. But so in conclusion, what I want to say here with all of this evolution is that we are clearly going in the direction of we're already there, in fact, that we have many core and distributed systems. So when it comes down to programming, this means 2 things. First of all, we need to do the asynchronous programming, and we cannot sort of hide it behind sort of a facade. We have to do it ourselves. We have to do it explicitly. And also, if we want our applications to be, responsive and all of this on top of this distributed flaky network, we have to be listening to failure handling and be aware of failure handling a lot more than, just thinking it's going to be fine. when you had a 3-tiered system with MySQL and Tomcat, something goes wrong. Probably most of the time you restart one of them and it's gonna start again, especially if they're co-located or if they're on the same machine. But if you're in a distributed setting, that's not the case anymore. If you restart one of them, all of the others are going to be like, hey, where did that guy go? So failure handling really is something we need to factor in as a first order concern in what we build. And so I think I've talked quite enough now in terms of theory. So let's go and let's build a small reactive web application. So what I want to build here is it's fairly simple. There's a view. It looks like this, the view. So it's awesome, right? You can see, I don't know, can you see it? So there's an input form and a send button. That's my view. Through WebSocket, it talks with the backend. And that's where you have message passing. There is an actor, which I will explain what that is in just a second, that takes care of this communication. And then on the other side, we have the Twitter API, and that does asynchronous HTTP. Our actor goes to talk asynchronously to the Twitter API. It could be any API. It could be a stream rather than a REST call, but this is the example I want to show you. We're going to explore two things here, which are tools for concurrent programming, an actor and a future, and a thing in the middle between both of them called a circuit breaker. And I could go on and show you 50 more things, but I won't have the time. So these are the 3 things I picked today, and I hope you're going to like that and find it useful. So let's get started with this. This is my project. Can you read this? Is the font size okay? Yeah, okay. So it's a small application written with the Play framework with Scala. I could write this in Java as well. All the APIs are also available in Java, so don't discriminate on the language here. It's just for this presentation, I choose this language. And here we have a controller which has an action, and that just shows this index file. And the index file looks like this. I have my input field up here and my send button. And down there I have a bit of JavaScript that sets up a socket, a WebSocket. When there is a message, it prints it out and appends it on the DOM. And then when I send something, I send it to the server. And that's all I'm doing right now. And this is what you see here. And the first step, what I want to do, I want to go in there and establish or build my WebSocket connection on the server side. So what I'm going to do here is I'm going to make a new class called WebSocket Client. And this thing is an actor. And an actor is this. An actor is a small thing, a small object. It's very lightweight, so I can have millions of them running on the same JVM. And each actor has a mailbox, and each actor has an actor reference, which is kind of an address to it. And what actors do is they send and receive messages to each other. What they also do is you can have a supervision hierarchy, which is really powerful when you want to do failure handling. I'm not going to talk about this today. But the most important thing really about actors is that they have state inside of them, and nobody else can look at that state. It's not like objects in Java where you have the getters and setters and everybody can mess up your state. Actors keep their state inside of them, and they send messages and respond to messages to receive in order to sort of react and alter the state. And if done correctly, then you don't end up having, you kind of eliminate completely the problem of global mutable state, because the state is hidden inside of the actor and nobody can touch it. So let's build this small actor. What an actor does, as said, is it receives messages. And what I'm going to say is if it receives a string, I'm going to first log this out. Received message. And here's my message. And so that's what I want to do here is I want to pong it back to the client. Okay, so in the Play framework, this the WebSocket communication, it's a dual-way communication. The way out is represented by a reference to another actor that the Play framework gives me. So what I do here, I get this reference, and then I say out, and I'm going to use this exclamation mark, which reads as bang. So out, bang, message. So, or I'm going to say, I'm going to echo this. Okay, so I'm going to just send it back. And I could write tell here. So the idea is this is a fire and forget thing. So you just say this and it runs and sends the message, forgets about it, doesn't wait for anything. So now I have a very simple actor that's just gonna reply to what I just send it. Then I need to set this up. So I'm going to set up a WebSocket. And then I say WebSocket accept with actor. And what I need to do here is I need to tell Play what type is going to come in and what type is expected to go out. And since I'm lazy, I'm not doing anything, I'm just going to use strings here. But I could use a parsed JSON value or ensure that there is some kind of type safety here. But I'm lazy, so I don't. And so what I'm doing here, WebSocket connection, first get the HTTP request, which asks for an upgrade call, and then you get back the socket. So here is my request. And then I'm saying, then the Play framework gives me an the outwards channel, which is the reference to the outwards channel. And so the last thing I need is a thing called props, which is a constructor for an actor, if you will, that can be serialized. And the reason for this really is just that you can use it in a clustered environment and send these things around. So I'm defining the props of the actor. And for this, I'm just say, you build an actor based on this out, and I will give you a class of my WebSocket client, and as an argument, I give it this out that you pass me in, and then I here say that I do that. And then I'm set up. The only thing I need now is in the routes file, where I route all of my HTTP calls. I say I get I get my socket here. And that should be enough for the Play framework. But now in our view, I also want to say something. So again here, I need to communicate it the address of the WebSocket. Otherwise, I'm not going to get anywhere. Application socket. And then I say WebSocket URL. And this is type safe, which means that if I ever change anything and it can't resolve it anymore, it's gonna blow up. So that's nice when you have a large application. It avoids errors. So let's see, will this work? Let's reload. Let's reload my water. And now I'm going to send it a message. Let's see. And I'm not getting anything. So that's a good sign. Or not. Nope, I'm not getting anything back. So let's see what I forgot. Oh, I have one error here. Huh. So you see, that's the fun thing when you have live demos, is oftentimes something goes wrong. I accept this, I get this. Well, let's see. I'm going to cheat here. Yeah? Oh, thank you. Yes, that was it. Great spotting this. And the Play framework did not complain. It should have failed the compilation, obviously. So let's see. Ping. Will you pong? Oh, yes. Great. So this worked. The first step. Wow. Cool. Okay. Let's move ahead and do the connection with Twitter then. Do you have any questions at this point, or? Nope. Okay. So I want to go and do my connection to Twitter. And I'm going to go ahead anyway here. I'm cheating a bit, but all I did is moving this in another file. if I want to talk to Twitter, what I need is I need to authenticate myself because, yeah, I need a OAuth request. I need to sign my request. So instead of boring you, I'm just going to go ahead and import this. These are the credentials for Twitter, okay? I'm reading them out of a configuration file, but this is going to help me build my request to Twitter. So let's go ahead and do this. I'm going to use a thing called the WS library that the Play framework has to offer. It stands for web service. And in there, I'm just putting an URL. I'm going to change this URL probably because I suspect the internet to be down. Let me check. Oh, it's there. Okay. So we can't even, in case there is no internet, I build a fake Twitter API because I had this already on a conference. So I have a fake Twitter in case this doesn't work. So I'm going to sign my, no, before I sign, I will say, as a query string, as a query parameter, I'm passing in whatever message I receive so I can filter with that message. Then I'm going to sign my request. I'm using an OAuth calculator that the Play framework gives me, and then I need a key and a token, and these I will import from the credentials I have here. So I just say in case of a key and a token, I want to use these, and so I take all of this, I move it up, and there I go, and then I do a GET request, okay? And that's all nice, and what this is really is a thing called a future. So this is not gonna reply with a response, this is gonna give me a future of a WS response, of the response. A future is a small thing. It's kind of a box, and this box can either eventually fail or succeed. So if it succeeds, it's going to contain the type that we expect. And if it fails, then it contains no value, but it keeps in mind the failure. It keeps in mind the exception, the throwable. It doesn't throw it out, it just keeps it. What you do with a future is doing a short-lived async computation. HTTP call, a database call, something like this. And you do it only when you don't do 100% CPU operations. If you only have something that involves the CPU, it makes no sense. So you want to use it when you have I/O happening, network or disk or whatever. Otherwise, it doesn't make sense to use a future. And so the nice thing is that while the future evaluates, while your network call is being answered, there is no thread involved. The thread is not blocked anymore. The thing that schedules the execution of this task can liberate the thread and let someone else use it. And when the operating system, through the select call, comes back and says, hey, I have something for you, then it will wake up and resume. And at scale, this really matters. So let's use this future. Response.map. So here I have my I have my response, and what I want to do as a first thing is I'm going to send it out. I'm just going to use the body of my response. I'm one level too high. Out. I'm using the body here. I'm just going to send this out and see what happens. So let's reload this. And this fails utterly, and Safari crashed, and the world is really bad. So what this tells me, and now you cannot, oh, yes, I can zoom in, cannot find an implicit execution context. Oh my God. So what is this? Well, a future is something that you need to schedule against something that's going to run it, as I said. It's like a thread pool, really, but a bit more fancy and a nicer name. And most of the time it's backed by the fork join thread pool anyway. So what you need is an implicit execution context. Implicit in Scala just means it's a way to say, instead of passing it in here explicitly every time I need one, I could do that. But if it's implicit, if it's in the implicit scope somewhere, it's gonna fetch it from there. So this is what I'm gonna do here. I'm going to say implicit val execution context. And so I could configure one, fetch one, but I'm inside of an actor. And since I'm inside of an actor, this guy already has one because the actor itself also needs to run their work. So the actor has a context, and the context has a thing called a, what's it called again? Dispatcher, yes. So this is an execution context, and I'm just gonna reuse that one. So if I reload now, this should compile. I cannot zoom in anymore because since this crashed, it doesn't let me zoom in. Well, well, I'm gonna zoom it like this then. So what do you search when you search for things on Twitter? Yes. I'm gonna search for a cat or a kitten. I could search for a kitten. Yes, here we go. Isn't that great? No, it's not because I can't see anything. So let's go ahead and extract this. Make this a bit nicer. So what I'm doing here is the same thing really. The only thing I did here, I'm parsing my JSON and I'm extracting the text of the tweet. So now if I reload and I look for kitten. So if I look for kitten, yeah, here we go. And you always find some Chinese or Japanese, I don't know what, but you always, it always goes like this. So we have our kitten, this works. Now let's suppose that for some reason Twitter was down. Now for this demo, I tried to tell them, please, when I call you, could you just, but they didn't want this. So I'm gonna simulate Twitter not being there or something, my network being slow. So there's a tool on most operating systems that can really slow down your network bandwidth to a bare minimum, like to a GSM. That's also very useful when you're testing a system because that shows you the experience that mobile users have when they have bad coverage. But for this, I'm just gonna cheat here and I'm just gonna say, when I'm making my call, I'm going to expect my request to be answered in 1 millisecond. So that's game over for pretty much any network out there, including the ones in the data centers of Twitter. So what do you think will happen when I'm running this now? What will we see on the screen or in the console when I'm reloading and searching for kittens? Anyone has an idea? So I see a blank page, yes, but in the console, what will I see? Sorry? Request timed out? Is probably what's happening, but any other? Nope. Internal server, the typical 500. Well, the truth is, you don't see anything at all because you receive the message and we have a future, and the future captures your exception. So since it captures the exception, it's not going to be thrown anywhere. It's just going to fail silently. So when you start working with futures, that's great because you don't know what's going on and where it fails. That's beginner mistake 101, and that's really frustrating, really frustrating. So what you do every time you work with a future, or when you have a chain of futures, at the very end of your chain, always recover it. If you don't recover it, it's going to fail silently, and that's horrible. So here I'm going to match all the failures that are not fatal. What are not failure? Not fatal failures. Not fatal failures are a special kind of matcher that Scala gives me, and that's not going to match out-of-memory exceptions or things like you cannot possibly recover from. Then it makes no sense to try to catch them anyway. You're busted anyway. There is no way you can recover from this. When the JVM says goodbye, well, you know. So in this case, I'm just gonna say that something went wrong, and I'm just gonna send that out to my client. And if I want the client to be able to work with this, since it expects some JSON, I will return. I will, work around. This is a hack usually. What I should do, I should define a protocol, and then in the protocol I should have an error condition, and then I catch the error condition. But I don't want to do this here. I'm lazy, so I'm just catching this. And when something goes wrong, I just append. I catch any kind of exception, and I'm saying that I'm displaying whatever the server sends me. Well, let's see if that works. So I want to zoom in. So zoom out. I cannot zoom in. Do you see? I'm not making this up. So just, you know, I'm trying to be nice here, but you know, I cannot zoom in. So I will have to zoom in dynamically every time. It's gonna be nice. So I'm gonna search for cat now. And here we go, and we have our response from the server saying the request timed out in 1 millisecond. Oh my god. But here we go, and we have handled our failure, except I did it wrong. This is not how I should have done it. And the reason is that I'm inside of an actor. And so in all other cases where you have a future, it's fine, but if you're inside of an actor, you're in this paradigm of working with actors that send messages to each other. So if I'm in there, what I want to do in case of a failure, I want to use messages as well to handle my failure. And that's where we go and use a pipe. A pipe is a pattern that Akka gives you, and it's a bridge between futures and actors. Under the hood is just an anonymous actor. But what a pipe does is when the future has completed, so either it failed or it succeeded, it's going to send out the result to an actor. And this is exactly what I want to do here. I'm going to do the simple version where I send the failure result to myself, because I don't have any specific actor to send it to who could benefit from using this. But if I want to do this, the first thing I need to do is I need to define a protocol. That's the first thing you do. And you have to be really careful about designing the protocol. That's the most important thing. In this case, it's pretty easy. So I have a search response, and that's just a string in our case. And then I have a search failure, which is throwable. And that's my protocol, very simple protocol. And now instead of sending this out directly, I just transform whatever response my futures gives me. And here I get the result, and then here I take a failure, search failure, and I say get the message of, oh, actually I get the exception, okay? So here I go, and now I'm using this pattern, the pipe, and now this thing here, which is my transformed future, I can call it, because I'm not very creative. Transformed future, I'm going to pipe it to myself, okay? So I'm sending this to myself. So this becomes a message that I send to myself, which means that I need to handle it. Up there I handled the string case, which is pretty nice, but now I'm going to handle first of the search response. So there I go with my response, and there it's all nice, and I'm sending the response out to the channel. And then in case of a failure, I'm getting my throwable here, and I'm sending it out. And so in theory, if I did everything right, I should get exactly the same behavior, which is to say here it should fail. Yes, you see there is only one line. And then if I remove this guy here and I reload, then I get my cats. Yes, lots of Chinese, Japanese tweets, I don't know. I cannot read this. All right. So that's sort of the failure handling part. Now I want to talk about something quite one of the other cool things and useful things, I shall say, if you start using such a system on a production system, which are circuit breakers. This is typically when you're at home and you have your microwave oven running and your toaster and your dishwashing machine, and then, I don't know, for some reason you plug in the hair dryer and then doosh, all the lights go out. This is what a circuit breaker does. It's inspired by this idea of a real circuit breaker. And it's there to prevent cascading failure, a surge in the system. You don't want everything to blow up or the whole house to go down just because you had all of these things running at once. And it's the same idea on a system where you have, say, legacy components or slow systems, and suddenly you have a web application in front of it, and it gets flooded by all of these requests. And that after a while, there's failures, it starts to time out, and you want to prevent this from propagating. And you can even have, so that's, then you start using circuit breakers. So Kevin Weber from Lightbend, he, prior to joining the company, Lightbend is the new name of TypeSafe, which is sort of behind Akka, Play, etc. And there is a cool webinar on their website on how they use this as Walmart in Canada. They redid the whole front-end website and portal, etc. with Play, and he explains how they use these circuit breakers in order to make the system appear as going smoothly, even though some services were overloaded in their legacy backend system. So this is really a quite useful thing. This is what I wanna show it to you. So this is really simple. It's closed, everything is great. Then it trips because it failed a number of times or it didn't respond in time for some time. Then it tries slowly to attempt its reset. So it's half open, so it's back, but it's not confident. It's, it may slash back faster. And after a while, it's confident enough, and it's going to be resetting itself and be closed again. So I'm going to build one of these guys here. I'm going to build a breaker. And for a breaker, I need a scheduler for it to know what time it is. And I'm just going to use the one that the system gives me. I need the maximum of failures. I want a maximum of 2 failures. The call timeout that my system can have while I'm giving it 5 seconds. The reset timeout, I'm going to give it 5 seconds as well. And so now I need to tell it what it should do with the seconds. And now it knows what a second is. Okay, so I have a breaker. And the breaker, I just plug it between my system and the call. So I will plug it between the call out to Twitter. Because, I could overload Twitter with all of my kitten requests here. And the way to do this is I'm going to say breaker with circuit breaker. And I pipe it to myself. However, here, I did some error handling. And that's not, I don't want to do this anymore because I want to fail so that my thing can trip. So I'm just removing the whole recovery part here. When this future fails, the breaker will trip. So here I introduce my failure again with request timeout of 1. And, oh yeah, because if I only do this, you will not see anything. So there are some callbacks here. I'm just gonna say print some things on the console so that we see that it's that something is happening. So breaker, half open, hang in there. And then on close we're happy. All right, so I have my sort of 3 things here, 3 states. I'm reloading. And okay, let me do my calls. So I'm just gonna query for cat 1 time and 2 times. And now on the console, you see that the breaker is open. Okay. So now after a while, it attempts to reset itself, so it's half open. Now I'm doing more calls, and it fails again because, well, it didn't really recover in there. And I'm going to be stuck in this infinite loop here if I don't do anything. So I'm going to cheat. I'm going to say my timeout is by default 1 millisecond. And that's not really how you should do it. I'm just doing this so I can show you that it eventually closes, right? When it's half open, the timeout is promoted to 1 second. and I'm going to use this timeout here. So what will happen next is it will fail, it will be open. Then after a while, it will be half open, and then it will reset its timeout to 1 second, and then it will be closed again. So I'm going to send it messages continuously. And in theory, this is what should happen. If it doesn't happen exactly like this, it means that it had a failure or I clicked too fast. You know, there's these two things, this 5 seconds timeout and these two failures. So let's go and see what happens. I have my console here, down there, okay. 2 cats, and the breaker's open. I send it more messages. It's half open. I send it even more messages, and it's closed, okay. So it's kind of works as designed. This is a really poor example because I'm here with my finger clicking. This is something you use when you have tons of requests trashing your system. Well, not tons, but I mean, it depends on the threshold of the system you're trying to protect. So if that system cannot handle more than 10 requests per second, you should set it to this kind of failure. This is something fairly experimental that you discover and practice in your deployment. So you have to turn the knobs a bit before this works well, but it really helps you, this pattern, to protect things. Okay, do you have any questions at this point? No questions? Okay. I think we have a bit more time. Yes, we do. So since we have a bit more time, I will talk a bit about deployment strategies. All of what I said in the beginning with the network failing, etc., means that you need to deploy this in such a way that it can scale in and scale out. So you can run a Play application and all of these applications. You can run it on your own. You can generate a Docker container and put it somewhere. You can generate a zip file. But if you really are serious about this, it's not trivial to do a elastic fault tolerant kind of deployment. Unless you have your own ops team, that's great. Maybe it's a good alternative to use a managed service or a solution. So there is one thing, and this slide is out of date. It's not a light band conductor. This is a thing you can use that sort of does automatic cluster management. But that's not the reason why I'm showing it to you. And I'm not being paid to show it to you either. The reason why I'm showing it to you here is the really interesting thing here. I mean, from an engineering perspective, not from, is this network partition resolution. There is a blog called afear.com, or, there is a series of blog posts called Call Me Maybe, after the Jepsen series, Carly Rae Jepsen, she sang this song, Call Me Maybe. And what's done in this series is you take a system, MongoDB, Elasticsearch, you name it, everything that says it's cluster, automatic failure handling, magic recovery, etc. And then you have a network partition, a real one, like the network is gone. What happens then? Well, in most cases, your cluster, you have a few nodes that are isolated, and then how do these guys know that they're offline, that they're cut off from the network and not the rest? So what happens in most cases is nobody goes down, and then the network partition is over, and you end up with inconsistent data because from the outside things wrote. So this is something that you have especially in larger data centers, or when you have separate data centers and one is cut off, the link between them is cut off, etc. And detecting this is really hard. And the way they solved it in this is using CRDTs, which are commutative replicated data types, I think. It's a mathematical concept. It's counters that increment themselves. It's really hard and a really interesting engineering problem. And that's solved in there. So when one guy goes down, it knows I'm the one that's down, and it shuts itself off. It's not going to be humming around and making your data become inconsistent. So this is the interesting thing here. So that's one thing you can use for this kind of applications. It also manages Docker containers, so random things, not only the play akka kind of things. There is another provider which I use and which is fairly nice. It's called Clever Cloud. So there it's like the idea is fully managed, like Heroku. You just push your code to Git, and then you configure it and you say, I want that many nodes. Let me show you. I want between 5 and 20 nodes, and they should range from XS to L, where XS has, I don't know how much RAM, and you get the idea. It has more cores, more memory. But you define these ranges, and then this thing, when the traffic increases, will range out horizontally and vertically, automatically, depending on what's cheapest for you. And this is an outdated slide because they decreased their prices. So they got, I think you can start at €5 per month or something, which is really cool. I mean, that's cheap, right? But for a very small instance. And so these are, again, they're not paying me either. I should ask them for some beer. But I have really good experience with this, and this is something that Heroku doesn't have. Right? So Heroku is there for a long time, but they don't have this because it's really hard, again, to do this. It's an interesting and hard engineering problem. How do you detect that things go? So you can build all of this on your own if you use AWS or things like this. But building all of this on your own, again, it's a lot of work. So you might want to outsource this. And that's it. If you want, I can talk about load testing as well. I have a few more slides. Yes, no? Any opinions? Yes? Yes? Yes. So, how do you test a reactive application? Because you're not gonna use unit tests, or you can, but that's not gonna help you. What you wanna do is you wanna test, I mean, is it really reactive? Can it handle all of this load? So you wanna do load testing. One tool is called Gatling. It's an open source load testing tool built on Scala, Akka, Netty, and it fires at your application. And there's two phases. The first thing is you record. So what you do, you run Gatling. It acts as a HTTP proxy. So you set up your browser to use this proxy, and then you browse around in your application and click on things, fill in forms, act as a user. You can record several of these scenarios and sort of just simulating users. And once you've done this, you have these scenarios, and then you say, I'm using a scenario in the following way. So I start here, for example, I have nothing for 4 seconds. Then I ramp up 200 users in the time of 10 seconds. Then I add 10 users at once. Then I ramp up in different ways, randomize things. You can be really creative. You can get really, really creative when it comes to how you want to simulate your load. And you need it because nobody in the real world, nobody waits and, are you ready? Let's go and click at once. This is not a very realistic way of testing a website. When you do it with A/B and you run 1,000, 10,000 concurrent requests, this is not how your users behave. They behave differently, they click on different things, and so your application will respond differently. And when you run this, then you get nice graphs. So for example, the number of responses per second, and you see here suddenly everything goes to hell and everything is red and your users are not happy. Or you get the response time distribution, which is even more interesting. And you see that there's a few people, not many, maybe 5% that get responses over half a second. But imagine if you have 5% of 10 million users, you will have many, that's still a lot of people that will complain on Twitter saying that your website is down. So what you want to do when you build this kind of application, you want to make sure that this last percentile is as small as possible. You don't want people to have a bad experience with your application, and that's the hard part. So that's one. If you use a huge, massive instance or a huge machine, you can test your application like this. But if you really want to go nuts, you use something called bees with machine guns. There's a video there, but I'm not going to show it now. But it's called like this. I don't know. It's called like this. I'm not going to show this now. what bees with machine guns is a script. So you have a Python script, and you hand over your AWS EC2 credentials to that script. And that sounds like a really bad idea. Yeah, it's a config file, boto config file, so you sort of set this up. And my advice is, if you start playing with this, set the debug level to 2, because otherwise it doesn't, you end up spending a lot of time wondering why it doesn't work, if it doesn't work. But it boils down to this. This tool, and I'm telling you this now, what this does is, it with the EC2 access, it fires up as many EC2 instances, micro instances that it needs. Like you say, you have a swarm of 400 bees, and then you say attack. So what this does is it just fires at your poor URL. So in essence, I just told you how to do a distributed denial of service attack, and please don't quote me on this, and only use it for educational purposes and nothing more. Thank you very much. So this is how you really test this heavy work kind of attacks, where you can have many things. And I did this, and I got banned from, what was it? There was a service, I forgot, but there was a service I used that, and I used it in my book, and then I got an email from the admin, like, is this IP address you? And if you use this, don't forget to, after you say bees down, so this sort of takes the swarm back, but then you log in, then promise me, you log in on EC2, and you delete all these micro instances. Otherwise, they're still there, and then you get $150, I think I got as an invoice because I forgot to turn these things off. So if you play with this, make sure your micro instances, your bees, are deleted in the end, because otherwise it's getting expensive. So these are 2 ways you can use, and there's more ways of testing, but I don't have the time to go into this. If you have any questions afterwards, you can always come to me. And yeah, that's pretty much it. I hope you enjoyed this talk, and yeah, thanks.